Hey guys, and welcome back to another video. In this video, we'll be discussing the squeeze theorem. This is the second video of the calculus playlist here on this channel. Alright, so let's get right into it. So, the topic of this video is the squeeze theorem. So, what is the squeeze theorem? So, basically, I will just write what the squeeze theorem says first, and then we will discuss it in more depth. So, the squeeze theorem says that if you have functions g of x is less than or equal to f of x is less than or equal to h of x, and the limit as x approaches c of g of x equals limit as x approaches c of h of x equals L, then limit as x approaches c of f of x equals L. Right? Okay, so basically the intuition behind the squeeze theorem is like essentially suppose you have some functions h, g, and f. So suppose you have like h of x is this graph right here, right? And then this could be like g of x. Okay, and then you can have f of x like this. So basically, the limit as x approaches c of h of x is equal to the limit as x approaches c of g of x, right? Because they both intersect at this common point right here. But f of x is bounded between g of x and h of x. So therefore, if g of x and h of x approach the same value as x is approaching c, then f of x is also going to approach that same value as x approaches c, since it's bounded, right? So that's why it's kind of called squeeze theorem, because f of x is essentially like squeezed between h of x and g of x. So it has nowhere else to go besides L itself. Okay? So that's kind of like the geometric interpretation, like the intuition behind the squeeze theorem. Okay? So now let's, I will show you how this squeeze theorem is applicable. So a very important limit in calculus and in mathematics in general is the limit as x approaches 0 of sine x over x, right? So this is a very important limit in calculus. And the way that you find the limit, the way you solve it, is using the squeeze theorem. So I will show you how to find this limit using the squeeze theorem. So first, let's just consider the unit circle. So suppose this right here is a unit circle, right? So this point right here is 1, 0, right? And then let's say we have some ray like this. And remember from pre-calculus that this point can be generalized as cosine theta and sine theta, given that this angle right here is theta, right? So then let's consider the extended triangle. So I will put this over here. So this is cosine theta, sine theta. And then let's see if we extend this triangle like this. We get like this right triangle right here, right? So what is this point? Well, we know that this length right here is length 1. So let's just call this vertical length x, right? So then now we can use our trig functions. So if we consider tangent of theta, we know that's equal to opposite over adjacent, so that's x over 1, which is just x, right? So the x coordinate of this point is just 1, right? And then the y coordinate of this point is just x, which is equal to tangent theta. So therefore, this point right here is 1 tangent theta. Okay? Cool. So now we will find the area of this big triangle that we just made. So the area of that triangle, so we have this triangle right here. So this length right here is tangent theta, and then this length right here is 1. So by the area of a triangle, it's 1/2 base times height. So the area of this triangle is equal to tangent theta over 2, right? Now, next, let's consider the area of this sector. So we have this sector right here. Right? So let's find the area of that sector. So this sector right here. I'll just shade it in for you guys. So it's this area right here. Okay? So what's the area of a sector? Well, it's just theta out of 2 pi times the area of the whole circle, which is pi r squared. So basically, pi r squared is the area of the whole circle, and then theta over 2 pi, that's like the fraction of the circle that the sector makes up. So this is like theta radians out of 2 pi total radians in a circle. Okay, so then notice that the pi's can cancel, and so you're just left with 1/2 theta r squared. So our circle, we have the unit circle, so that means that the radius is equal to 1. So then we have 1 squared, which is just 1. So therefore the area of this sector is just 1/2 theta, or theta over 2. Okay? So that's the area of the sector. Now, finally, let's consider the area of this smaller triangle made by that dotted line, right? So you have the area of the sector, and then you have this small piece that we're just going to remove, and then now we have a triangle, right? So essentially, we have this triangle. So if we just remove that piece, now we have this triangle, right? So I will find the area of that right here. We have this. So we know that this bottom base length is 1, and then the height of this triangle, the altitude is what? Well, we know that this point right here is cosine theta, sine theta. So what that means is that the length from here to where the altitude intersects the base, this length right here is cosine theta, and then the length of the altitude itself is sine theta. So the length of the altitude is sine theta. And so then by the area of a triangle, 1/2 base times height, we have that the area of this triangle is sine theta over 2. Okay? So why did we find the areas of all these shapes? Well, it's so that we can create that bound. Because remember, in the squeeze theorem, we require 3 separate functions where each one is successively less than the other one. So we know that this area must be smaller than this area, because this shape is inscribed in the sector, right? The triangle is inscribed in this sector, and then the sector is inscribed within this bigger triangle. So this area is less than this area, which is less than this area. We know that for sure, just geometrically speaking. So we can write that sine theta over 2 is definitely less than or equal to theta over 2, which is definitely less than or equal to tangent theta over 2. Okay, and so now we have our 3 functions with the successive inequalities. Alright, cool. So now I'm going to multiply all sides of this inequality by 2 over sine theta. Okay, and so then what do we get? Well, sine theta over 2 times 2 over sine theta, that's just 1, as less than or equal to, and then theta over 2 times 2 over sine theta, that's just theta over sine theta. And then tangent theta over 2 times 2 over tangent theta. So the 2's cancel, and then remember that tangent is equal to sine over cosine. So we have sine theta over cosine theta, right, times 1 over sine theta. So then the sines cancel, so you're just left with 1 over cosine. Alright, cool. So now, if we take the reciprocal of all the sides, inequalities flip. So then we get that cosine theta less than or equal to sine theta over theta less than or equal to 1. So now this is perfect, right? Because we have our function that we want the limit of sine x over x, sine theta over theta. It's the same thing. And then we have bounded it between two other functions. So that's exactly the setup that we need for the squeeze theorem. But remember, there's still one important part left that we need to establish before we can use the squeeze theorem, which is the limit of cosine theta and the limit of 1 must be the same when x approaches 0. And it's very easy to show that, right? Because if we take the limit as x approaches 0 of cosine x, this is just equal to cosine 0, right? You can just simply substitute in 0 because cosine x is continuous at x equals 0, and cosine 0 is just equal to 1. And then the limit as x approaches 0 of 1, the limit of any constant function is just the constant function back. So this is just also equal to 1. So therefore, the limit as x approaches 0 of cosine theta and 1 is they're both equal to 1. So therefore, by the squeeze theorem, the limit as x approaches 0 of sine theta over theta is also equal to 1. So this limit right here is equal to 1 by the squeeze theorem. Okay? So this is just like basically how you can use the squeeze theorem to help find limits. Because remember, like if we notice that if we just tried finding the limit without using squeeze theorem, we would run into a problem immediately because we'd have to substitute in 0 in the denominator, and so we get like a 0 over 0 situation, right? Because sine 0 is 0 and then 0, so 0 over 0, indeterminate form. So therefore we have to use the squeeze theorem. Alright, cool. So let's do some more practice problems like this using the squeeze theorem to solve the limits. Alright, so technically that was example 1, so this will be example 2. Alright, so consider the limit as x approaches 0 of x squared times sine of 1 over x, right? So notice that if we just substitute in 0 for x, we have 0 times sine of 1 over 0. So 1 over 0 is undefined, right? It's not properly defined, so therefore we can't substitute in 0, so we have to use a different method. So let's try applying the squeeze theorem, right? Let's see if we can find some bound on this function. So we know that sine of 1 over x is bounded between a negative 1 and 1, right? Sine is bounded between negative 1 and 1. And then we want x squared times sine of 1 over x. So let's just multiply all the sides by x squared and see what we get. So we have negative x squared is less than or equal to x squared sine of 1 over x is less than or equal to x squared, right? So now we have bounded our function between negative x squared and x squared. So now as long as the limits of negative x squared and x squared are equal to each other, then we can just simply apply the squeeze theorem and we can find the limit of this, right? And indeed that is the case, right? Because if we take the limit as x approaches 0 of negative x squared, this you just substitute in 0 and you get 0. And then similarly, if you take the limit as x approaches 0 of positive x squared, again you just substitute in 0, so you get 0 squared, which is just 0. So because these two limits are the same and they're 0, so that means that this original limit will also be equal to 0 by the squeeze theorem. Alright, nice. Alright, we will do another example. So we have the limit as x approaches 2 of f of x, right? And we're given that 4x minus 3 is less than or equal to f of x is less than or equal to x squared plus 1. Alright? So this one you might be like, how do we even find the limit, right? Because we don't even know what f of x is. We only know that f of x satisfies this inequality. So you might think like it's impossible to find this limit because you don't even know what f of x is. But actually, you can just try finding the limit of the other functions, because you know you have 4x minus 3 and x squared plus 1. So let's see what happens if we find the limit as x approaches 2 of these functions. So if we find the limit as x approaches 2 of 4x minus 3, 4x minus 3 is continuous at x equals 2, so you can just substitute in. So we get 4 times 2 minus 3, which is equal to 5. And then similarly, let's find the limit as x approaches 2 of x squared plus 1. So again, x squared plus 1 is continuous at x equals 2, so you can simply just substitute in. So you get 2 squared plus 1, which is also equal to 5. So there, we've showed that the limits as x approaches 2 of 4x minus 3 and x squared plus 1 are the same, namely they're both 5. So therefore, by the squeeze theorem, the limit x approaches 2 of f of x must equal 5, right? This must equal 5 by the squeeze theorem. So you don't even have to know what f of x is. You could just find the limits of the outside functions, and then you can automatically find the limit of f of x just because of squeeze theorem. So this is how the squeeze theorem is very helpful sometimes, right? But yeah, that pretty much wraps up this lesson on the squeeze theorem. If you found this video helpful, please make sure to leave a like and don't forget to subscribe. I'll see you guys in the next video.